Welcome. Today we shall continue our discussion of black holes of general relativity. In this lecture, I shall discuss two of the most profound and revolutionary discoveries since Einstein formulated his new theory of gravity more than 100 years ago. I'm referring, of course, to the discoveries by Roger Penrose and Stephen Hawking. So let us begin. We concluded, or rather Oppenheimer and Snyder concluded, that when a massive star exhausts all its supply of nuclear fuel, it has no option but to collapse and become a black hole. All that persists is its gravitational field. Now let us ask, what is inside the black hole? The answer is, there is absolutely nothing inside the black hole. Well, not quite. Let us recall what Oppenheimer and Snyder said in their famous paper of 1939. The star thus tends to close itself off from any communication with a distant observer. Only its gravitational field persists. Once a star collapses to the critical radius, the Schwarzschild radius, 2gm by c squared, it cannot arrest its collapse. According to general relativity, one can state exactly that it will continue to collapse till it becomes of zero radius and infinite density. Therefore, in a sense, there is nothing inside a black hole. But there is. After creating the black hole, the spherical star continues imploding to infinite density and zero volume, whereupon it creates and merges into a space-time singularity. If you have studied a little bit of complex variable, you will know what I mean by a singularity. The function 1 divided by z minus z naught is singular at z equal to z naught because its value becomes infinite. So what we are saying is that there is a space-time singularity which corresponds to the star having been squeezed to zero volume and infinite density. So if you ask the question once again, what is inside the black hole? The correct answer is to say that there is a space-time singularity. This was obvious from Oppenheimer and Snyder's paper. But very few people believed in the results of Oppenheimer and Snyder. As I discussed last time, Eddington, already in 1935, had dismissed Chandrasekhar's great discovery because it led to the formation of black holes, and Eddington knew that once a black hole forms, the singularity is inevitable. In 1939, Einstein wrote a paper in which he claimed that the Schwarzschild singularity is not physically realizable. And therefore, most physicists followed Eddington and Einstein, and they just didn't believe what Oppenheimer and Snyder had found. John Wheeler, who was to later on coin the phrase black hole and became the messiah of black hole physics, went around the world dismissing the results of Oppenheimer and Snyder. His point was that general relativity must surely fail inside a black hole. Quantum mechanics will prevent the formation of the space-time singularity. So this is where matters stood when physics resumed in 1946, soon after the end of the Second World War. But John Wheeler was a little bit perturbed that one hasn't said the last word about Oppenheimer and Snyder's paper. Therefore, he persuaded three young physicists by name Colgate, White, and May, working at the Los Alamos laboratory, to do a proper calculation using a computer of the collapse of a non-rotating star. But this time, unlike Oppenheimer and Snyder, they included pressure, nuclear reactions, shock waves, heat, radiation, mass ejection, everything that you can think of in their calculation. Now, why was it that they were able to do these calculations and nobody else was able to do these calculations? Two reasons. One is Los Alamos had the world's most powerful computer at that time. Secondly, Los Alamos was where the hydrogen bomb project was initiated. Therefore, all the computer codes that went with the hydrogen bomb development were available to scientists in the Los Alamos laboratory because subsequent to the end of the Second World War, these codes had been declassified. So around 1960, Colgate, White, and May found, through really hard and honest computer calculations, the following results. When the star has a small mass, it formed a neutron star, and the formation of the neutron star triggered a supernova explosion. But more massive stars produced black holes. And they recovered all the features of Oppenheimer and Snyder's result. So this was around 1960, 1961. In 1963, one of the most important discoveries in the entire history of astronomy was made, the discovery of quasars. Soon we shall discuss that a few lectures from now. But right now, please accept the following statement. Soon after quasars were discovered, it became clear that the central engine that powers quasars must be supermassive black holes. Nothing else could explain this phenomenon. Therefore, black holes which had been buried quietly were resurrected. In December 1963, in Austin, Texas, there was a very famous international symposium to discuss the newly discovered quasars. There, in a public lecture, John Wheeler spoke with great enthusiasm and passion about the 1939 calculations by Oppenheimer and Snyder. By now, he had become absolutely convinced that Oppenheimer and Snyder's results were not as a result of artificial assumptions they had made about spherical symmetry and so on, but this would be true even in a realistic collapse. Oppenheimer was at that important meeting, but he was not attending the various talks in the parallel session. Instead, he was sitting in the lounge talking to old friends whom he had not met for a long time. He had lost all interest in physics and physicists, but he knew all along that although everyone in the world doubted his results, that he was right. Now, you may be a bit mystified by the statements that I am making over here. I very strongly urge you to read the biography of Robert Oppenheimer. He was undoubtedly one of the most brilliant theoretical physicists of the 20th century, but it is also an incredibly tragic story and a sad commentary on human beings. So do read. I will ask Dr. Sushant Konar to put in the reference to a recent biography of Oppenheimer. It is well worth spending some time reading it. But let us proceed. Soon after quasars were discovered, the golden age of black holes began around 1964. And the star of the golden age, or the beginning of the golden age, was Roger Penrose, a mathematician at Oxford. What he proved in 1964 was an exact mathematical theorem using topology. This was the first time topology had been used to prove any result in any branch of physics. He proved in a mathematically exact manner that every black hole must have a singularity inside it. Now, we know that there was a singularity in the center, at the center of the Oppenheimer-Snyder black hole. But that was a spherically symmetric, non-rotating star collapsing. It is very easy to envisage a singularity will indeed form at the center of symmetry. But what if the star was not spherically symmetric? What if there were giant distortions? What if the star was rotating? Is it still obvious that there must be a singularity at the center? It was not at all obvious. And that is why people doubted the result. But this result of Roger Penrose was an exact result and independent of any assumptions that you make. This statement by Roger Penrose, namely every black hole must have a singularity inside it, was a statement with sweeping power. It did not deal with idealized imploding stars. It did not assume that any random deformations on the star were very, very small. It dealt with every imploding star imaginable. It dealt with stars that populate our universe. And I have quoted this from Kip Thorne. So what Roger Penrose proved in a mathematically exact manner, without making any assumptions whatsoever about the symmetry of the collapse or the absence of symmetry in the collapse, that there must be a space-time singularity inside a black hole. This was extremely disturbing to physicists because they asked the question, what if that singularity was not inside the black hole? What if that singularity was formed outside the black hole? Physicists don't like singularities because they don't know how to deal with singularities in physics because you don't know what went into that singularity. So singularity spells danger to physicists. So the question was, can there be a naked singularity outside of the event horizon? Roger Penrose spent many years trying to construct mathematical models where a singularity will form outside the black hole. He never succeeded. Of course, he couldn't make this a rigorous statement, but he never succeeded. But he was sufficiently confident that in 1969, he stated the famous cosmic censorship principle, which says that no imploding object can ever form a naked singularity. If a singularity is formed, it must be clothed by an event horizon so that no one in the external universe can see the singularity. So you hide the singularity by the event horizon. So this theorem till today has not been proved mathematically rigorously, but it seems like a very reasonable theorem to accept. Now let's proceed. Many years later, 60 years later, almost 60 years later, in 2020, Sir Roger Penrose was awarded the Nobel Prize for Physics, and the citation read as follows: "Formation of black holes is a robust prediction of Einstein's general theory of relativity." So the formation of black hole is not an artifact of simplifying assumptions that Oppenheimer and Snyder made at that time, but it is a robust prediction. And this was considered sufficiently important that 60 years, nearly 60 years after the discovery, they awarded the Nobel Prize for Roger Penrose. Now, the next revolutionary discovery. In the previous lecture, I told you about the discovery by the New Zealand mathematician Roy Kerr of the metrical spacetime around a rotating star. What young Brandon Carter, who was a student in Cambridge University, classmate of Stephen Hawking, Martin Rees, and various other people at the time, proved a very important theorem. He showed in a mathematically exact manner that the Kerr solution represents not just one special type of spinning black hole, but every spinning black hole that can possibly exist. In other words, every spinning black hole in the universe must be describable by the solution that Kerr obtained for Einstein's equation for the space-time geometry surrounding a rotating body. And then came a series of mathematical theorems, exact theorems, which have been grouped together and called the No Hair Theorems. The statement was first made by John Wheeler that black holes have no hair. What did he mean by that statement? What he meant by the statement can be, let me illustrate what he meant by the statement by taking a couple of examples. Let us consider a star. Most stars are endowed with a magnetic field. The sun has a magnetic field. Suppose the star collapses and forms a black hole over there. Will the black hole have a magnetic field? We said when the star core collapses and forms a neutron star, the neutron star will have a magnetic field strongly amplified, 10 to the power 12, 13, 14 Gauss. Will the black hole have magnetic field even stronger than a neutron star, or will it not have a magnetic field? It was proved in a mathematically exact manner that the black hole will not have a magnetic field, even though the star that collapsed and formed the black hole had a magnetic field. So one of the hairs that black hole does not have is a magnetic field. Let's consider another case. Let the star have a little mountain on it, a little bump. Will the black hole have a little pimple on it, or will the black hole be spherically symmetric? It was proved in a mathematically exact manner that no, the black hole will be perfectly axisymmetric. There will be no bumps or mountains on the black hole. And then came the most spectacular of the No Hair Theorem. The theorem by Brandon Carter, Stephen Hawking, and Werner Israel proved in 1972. They proved in a mathematically exact manner that black holes are uniquely characterized by their mass, charge, and angular momentum, and nothing else. So let me repeat again. Black holes are uniquely characterized by their mass, charge, and angular momentum. And since charges are irrelevant in the context of an astronomically formed black hole, therefore, it is fair to say that black holes are uniquely characterized by their mass and angular momentum, nothing else. But you'll say, but look, the star had many attributes to it. What happened to all of that? So let's discuss that. All the deformations the star may have had are radiated away as gravitational waves. So by the time the black hole settles down to a stationary state, it does not have any deformations. Now please remember that inside the star there are nuclear reactions taking place. We discussed the energy generation of the stars. And there are all kinds of quantum numbers particles have. Particles have baryon number, lepton number, strangeness, isotopic spin. There are all kinds of conservation laws that have to be satisfied in physics. What happened to all those attributes? The black hole doesn't seem to have any of those attributes. In other words, you cannot tell the difference between a black hole formed entirely of electrons from another one of the same mass formed entirely of protons, and another one, as John Wheeler would say, formed entirely of television sets, or another one formed entirely out of collapse of motor cars. You cannot tell the difference because the black hole is characterized only by its mass, charge, and angular momentum. All other attributes of matter have disappeared. Almost all the conservation laws discovered in the last century, are they violated by the black hole? No, I don't think physicists would like to use that word. They will say they are transcended by the black hole. Those conservation laws are not applicable to black holes. Now, this theorem sent shockwaves, and the most eloquent expression of how shocking this result was by Chandrasekhar. Let me quote partially. In my entire scientific life, the most shattering experience has been the realization that an exact solution of Einstein's equation, the Kerr metric, provides the absolutely exact representation of untold number of black holes that populate the universe. In other words, every black hole in the universe can be described by the Kerr solution, because all that Kerr solution needs is the mass and angular momentum. It doesn't care about any other attribute of matter. So, let me repeat. The Kerr solution provides the absolutely exact representation of the untold numbers of massive black holes that populate the universe. Why Chandrasekhar regarded this as the most shattering experience is that if you consider a small piece of chalk piece, we cannot give an exact description of the small piece of chalk piece. We cannot give even an exact theory for the helium atom, which consists of 2 electrons, let alone a solid which consists of 10 to the power 23 electrons per cubic centimeter. And here we are saying we can describe mathematically exactly every black hole in the universe. That is a shattering statement indeed. And then came the quantum twist. Now listen to these arguments very carefully because they are fascinating and they are very profound. The first argument came by a young student of John Wheeler at Princeton University by name Bekenstein. He argued that black holes must have entropy. He argued that the entropy of the black hole must be proportional to the surface area of the black hole. Surface area of the black hole is 4 pi r squared, where r is the Schwarzschild radius, 2gm by c squared. So the entropy of the black hole must be proportional to the area of the black hole. Can you say something about the constant of proportionality? Well, I would not belabor what is written here. I would like to simply say that using dimensional analysis, which I have sort of hinted here, but please don't bother about the detail. Using purely dimensional analysis, Bekenstein was able to show that the entropy of the black hole is related to the area of the black hole by this proportionality constant, which is Boltzmann's constant, cube of the speed of light, divided by 4 times Newton's constant of gravity and Planck's constant, h bar. Now this is a shocking result. Let us go back from 1972, well, before that. So what Bekenstein argued was that the entropy of a black hole cannot be 0. The entropy of the black hole must be proportional to its surface area. The larger the mass of the black hole, larger is the surface area, 4 pi r squared, therefore larger must be the entropy. And the entropy can be calculated using this formula. And Bekenstein said, if you had a black hole of 10 solar mass, then its entropy will be truly astronomical, 10 to the power 79, which is an incredible amount of entropy. If you remember what entropy represents in statistical physics, it represents loss of information. Now let's go back to 1900. What was the main problem in 1900? Black body radiation could not be fitted into classical thermodynamics. And Max Planck solved this problem in 1900, and that was the birth of quantum physics. In order to unify thermodynamics, classical thermodynamics, with classical theory of radiation, he had to introduce a new constant, h, which we now call as Planck's constant. That is the essence of quantum physics, Planck's constant. Now, what is it that we are finding? Entropy of the black hole is related to the surface area. This is the constant of proportionality. The left-hand side is classical thermodynamics. The right-hand side is classical gravity. So what Bekenstein found was that if you want to marry classical thermodynamics with classical gravity, again you have to introduce Planck's constant. Absolutely extraordinary. So Planck's statement that H has to be introduced signaled the breakdown of classical physics and the birth of new physics, quantum physics. Therefore, it is reasonable to conjecture whether Bekenstein's discovery marks the beginning of a new era in which we shall discover a quantum theory of gravity. That's perhaps many years, perhaps even many decades away, but it is not unreasonable to speculate along those lines. But Stephen Hawking was extremely skeptical of Bekenstein's result because he argued that black hole cannot have entropy unless it is at a finite temperature. Now you look in any book on thermodynamics, it will tell you that an object, in order to have entropy, must be at a finite temperature. Why? A classical black hole absorbs everything. It's a perfect sink. It gobbles up everything and nothing can come out of it. Now, any object at finite temperature will not only absorb, it will also radiate appropriate to its temperature. But therefore, the only perfect sink can be an object at absolute zero of temperature. If a body only absorbs everything you throw at it and nothing can come out of it, then that object cannot be at a finite temperature. It must be at the absolute zero of temperature. And since where black holes gobbles up everything and nothing can come out of the black hole, the temperature of the black hole must be 0 Kelvin, and therefore it cannot have entropy. So this argument was going on. Meanwhile, there was a deep insight, and that came from Moscow in Russia. Zeldovich was a very great theoretical physicist in Russia. He made astounding contributions to many, many branches of physics, including hydrodynamics, the development of the hydrogen bomb, high-pressure physics, elementary particle physics, gravity, cosmology, you name it. He made the following argument. He said, if I have a metal sphere and if I spin it, it will emit electromagnetic radiation. You will say, why? Why should it emit electromagnetic radiation? Well, if it had a magnetic field, we know it will emit electromagnetic radiation. We discussed that when we discussed pulsar and Faraday's unipolar dynamo. But here we are not talking of magnetic field or anything like that. We are just spinning a metallic sphere. And here was Zeldovich's argument. He said a spinning metallic sphere will create outside it electron-positron pairs, neutron-antineutron pairs, proton-antiproton pairs. One particle will have positive energy, the other particle will have equal and opposite negative energy. And therefore, they come out of vacuum, and before you can catch it, they recombine. So they are what are known as virtual particles. Because if you could catch a particle with negative energy, that would violate all the laws of physics. But physics does allow for these virtual pairs of particle, antiparticle to come out of vacuum and annihilate themselves once again. But these virtual pair, let's consider this pair of particle and antiparticle, one with positive energy and another with negative energy, can materialize or can become real particles if I can make the negative energy particle become a positive energy particle. In order to do that, I must supply energy. Where will I supply energy from? The energy will come from the rotational energy of the metallic sphere. That is what Zeldovich's argument was. Therefore, he argued that virtual pairs of particles and antiparticles will materialize, will become real particles with positive energies by extracting energy from the rotational energy half I omega squared of the metallic sphere. Fine. You keep this in mind, and now let's get back to black holes. Before we do that, let us go to Princeton University in America in the year around 1954, where Robert Dicke, a most distinguished experimental physicist, also a renowned theoretical physicist, made a very important discovery, which was the forerunner to the discovery of the laser. He discovered the phenomena of superradiance by atoms. Superradiance is the following phenomena. Suppose I have a group of n excited atoms, where n could be a very large macroscopic number. And these excited atoms can interact with light in a collective, coherent manner to produce high-intensity light. In other words, an atom in excited state can jump down to the ground state and emit a photon. Another atom can do so, another atom can do so. But if 10 to the power 23 atoms can do it coherently, then the intensity of radiation you will get will be enormous. So this is stimulated emission, and this is, as I said, was the forerunner of the discovery of laser, which is light amplification by stimulated emission of radiation. That's what laser stands for. So this was the discovery of superradiance. And then around 1967, Roger Penrose made a very remarkable discovery. He discovered that there will be superradiance from spinning black holes. And this was a thought experiment. So what was the thought experiment? Let us go back to the Penrose process, which I discussed at the very end of the last lecture. A particle with positive energy enters the ergosphere of a rotating black hole, splits into two particles, one with a positive energy and one with a negative energy. The negative energy particle falls into the horizon and disappears from this universe. The positive energy particle with a greater energy now comes out of the ergosphere. So you have extracted energy from the rotational energy of the black hole. So that is the Penrose process. Now Penrose discovered an analogous phenomena occurs when electromagnetic radiation or gravitational radiation is incident on a rotating black hole, provided their frequencies are sufficiently small and the waves are incident on the rotating black hole in suitable directions. So what he's saying is that under those suitable circumstances, with suitable frequencies, if I have an incident radiation with intensity I of electromagnetic waves or gravitational wave, then the intensity of the reflected wave can be greater than the intensity of the incident wave. This is the phenomena of superradiance from rotating black holes. So radiation comes back with enhanced intensity, and it has acquired this enhanced energy from the rotational energy of the black hole. Now, in papers published around 1970, 71, and 72, Zeldovich in Moscow made the following absolutely extraordinary predictions. This is Penrose here. There will be superradiance from rotating black holes. Waves incident on a rotating black hole in certain modes, in certain directions, in certain frequency interval, will be scattered back with increased intensity. That is the phenomena of superradiance. Now, what Zeldovich said was, if I interpret the superradiance in the particle pictures, not as waves but in photons or gravitons, then this phenomena of superradiance discovered by Roger Penrose corresponds to stimulated emission. In other words, I stimulate a bunch of atoms which are phase coherent, and out comes stimulated emission from n atoms in phase coherence, which is superradiance. So Zeldovich argued that superradiance can be thought of as stimulated emission. So a rotating black hole emits stimulated emission. Now, here was Zeldovich's argument. Superradiance corresponds to stimulated emission of radiation. The rotating black hole has been stimulated to emit radiation at the same frequency and in the same direction as the incident radiation. Zeldovich argued that one should also expect a steady state of spontaneous emission in the superradiant mode. In other words, Zeldovich argued if there is stimulated emission from a rotating black hole, there must also be spontaneous emission from a rotating black hole. Why is that? Anyway, we'll come to that presently. In the summer of 1973, Stephen Hawking visited Zeldovich in Moscow. Now, this is a sad story. Zeldovich at that time was riding a big wave. He was making the most important discoveries in many branches of physics, including elementary particle physics and cosmology. But he was not allowed to travel by the Soviet authorities outside of Soviet bloc to present his results in conferences because he had worked in the hydrogen bomb project. Hydrogen bomb was made long before that. The war ended in 1945, and by 1954, the hydrogen bomb had been made. But 20 years later, Zeldovich was not allowed to travel outside of the Soviet Union. So what did people do? They went to Moscow to meet Zeldovich in his small two-room flat. If Zeldovich couldn't come, they went. Everybody who was anybody in physics went to visit Zeldovich. One of them was Stephen Hawking, although travel was very difficult for him already in 1973. He went there. And there, in a little blackboard in his room in Moscow, in his flat in Moscow, Zeldovich described his ideas to Hawking about spontaneous emission from rotating black holes in the superradiant mode. And then he asked Stephen Hawking the following question. Remember, Zeldovich had concluded that if there is stimulated emission from a rotating black hole, there must also be spontaneous emission from a rotating black hole. So here was the question. Will a non-rotating black hole also radiate spontaneously? Will a non-rotating black hole also radiate spontaneously? Well, let us now go back and remind ourselves of a very profound paper that Einstein published on the quantum theory of radiation in 1917. This is stimulated absorption. There is an atom in a lower energy level. A photon comes in and excites the atom from the lower level to the upper level. This is stimulated absorption. This absorption has been stimulated by the incident photon. And this is stimulated emission. An atom in the excited level is tickled by the incident photon to jump from the upper level to the lower level, emitting a photon of the same frequency as the incident frequency and in the same direction as the incident radiation. This is stimulated emission. But there is also spontaneous emission. If there is an atom, an isolated atom in a higher energy state, then spontaneously it will come down. The essence of Einstein's paper of 1917 was the following. Whenever there is spontaneous emission, there must also be stimulated emission. Why is there spontaneous emission? Well, Einstein did not know at that time. Today we know that an electron jumps from upper level to lower level even without being stimulated by electromagnetic radiation because of vacuum fluctuations. There are virtual particles being created out of vacuum, and this sort of tickles, these fluctuations of the vacuum tickles the atom to come from the excited state to lower state. But that's a different story. Let's not worry about it. What Einstein showed in this most important paper of 1917 is that there is a fundamental relation between absorption, stimulated emission, and spontaneous emission. It is this interplay between stimulated absorption, stimulated emission, and spontaneous emission that gives rise to Planck's distribution for the black body radiation. But that's a different story. Let us not digress into that. The important message that Zeldovich conveyed from the paper of 1917 is that whenever there is stimulated emission, there must be spontaneous emission. Whenever there is spontaneous emission, there must be stimulated emission. All right? So Zeldovich argued that since a black hole can be stimulated to emit, it must also spontaneously emit. But he only knew that you can stimulate a rotating black hole to emit, the phenomena of superradiance discovered by Roger Penrose. But his question to Hawking was, go and find out if a non-rotating black hole will also spontaneously emit. 1 year later, in 1974, Stephen Hawking made a very great discovery. The discovery was the following. He had answered Zeldovich's question. A non-rotating black hole will radiate, as conjectured by Zeldovich. It will emit particles and radiation in all modes, not just in the superradiant mode, because there is no superradiance for a non-rotating black hole. It will emit particle and radiation in all modes, as though it were an ordinary black body at a temperature T, which is proportional to the surface gravity kappa. Surface gravity kappa is what we call a small g, the acceleration due to gravity on the surface of the Earth. So kappa is the g m by r squared at the surface of the black hole. So he was agreeing with Bekenstein that the black hole will have a temperature. What convinced him of this was the following. Now here is the formula for the number of photons with frequency nu of black body radiation, that is proportional to 1 over e to the power of h nu over kt minus 1. You remember that's what comes in Planck's law. What he discovered was in the case of black hole radiation, the number of particles created in a mode with frequency omega, 2 pi omega is nu, is 1 over e to the power 2 pi omega by kappa minus 1. Therefore, the role of temperature is played by surface gravity kappa, which is the acceleration due to gravity on the surface of the black hole. Here is another result. In black body radiation theory, the probability of emission is related to the probability of absorption by this principle of detailed balance with this factor e to the power minus h nu over kt. In the case of a black hole radiation, the probability of emission is proportional to the probability of absorption by e to the power minus 2 pi omega over kappa. Kappa plays the role of temperature. Kappa is the surface gravity. Now, the important thing to appreciate is that even a stationary, non-rotating, spherically symmetric black hole will radiate. Where does the energy come from? The energy comes at the expense of the rest mass energy of the black hole. Therefore, as the black hole radiates, it will become less massive. Now, I do not want to take the time out to explain or make plausible why this Hawking radiation occurs. First thing to appreciate is that nobody had made any mistake in the past in saying that nothing can come out of the black hole. That was a statement made in classical physics. Now, what Hawking is saying is that quantum mechanics allows for this radiation to happen. So is this radiation something like alpha particle decay of radioactive nuclei? Remember, alpha particles come out of the radioactive nuclei. There is a huge potential barrier. Despite that, it comes out, and George Gamow argued that it comes out by quantum mechanical tunneling. Therefore, our particles coming out of the black hole, going through the event horizon, quantum mechanically tunneling their way through the event horizon? No, not really, because there are no particles inside the black hole. We had already concluded that. There is only a space-time singularity in the black hole. So how do you understand this radiation? Well, there are many ways. One of the ways to look at it is the following. Now, just as Zeldovich's rotating metallic sphere produced electron-positron pairs, you will say that the black hole outside the horizon and very close to the horizon produces particle-antiparticle pairs. One has positive energy, one has a negative energy. Let us say, to be specific, an electron-positron pair. Let us say the electron has negative energy, the positron has positive energy. Now the electron falls into the black hole, and what escapes is a positron with positive energy. Is this going to violate anything? No, because what physics tells you is you cannot catch a particle with negative energy in the world we live in. The electron had negative energy, but it has gone into the black hole, and you cannot detect it. Therefore, that's okay. So a positron goes out. Now, the electron has negative energy. The black hole has a positive rest mass energy, mc squared. Therefore, the negative energy cancels out some of the rest mass energy of the black hole. Therefore, the rest mass of the black hole decreases. So this is one way of understanding where these particles on radiation emanate from. So it is of quantum mechanical origin. Now, Hawking didn't like this result because he tried his very best to make this radiation go away. He tried every trick in his books to make this radiation go away, but it simply wouldn't. What finally convinced him was the thermal nature of the radiation. What convinced him was that the spectrum of this radiation is like black body spectrum. It is uniquely characterized by only one thing, namely the surface gravity kappa. Just as black body radiation is uniquely characterized by temperature and temperature alone. All other attributes of matter of the black body is gone. The radiation remembers only the temperature. Hawking's discovery is not mathematically rigorous. It makes sense. Why is it not mathematically rigorous? What Hawking did was the following. He treated gravity and therefore the curvature of space around black hole classically, according to Einstein's general theory of relativity. He treated particles and waves as quantum fields. So what he did was quantum field theory in curved space-time, which nobody had done before. Well, some people had attempted, but nobody had produced any spectacular result out of those calculations. Normally, quantum field theory is done in flat space-time. But here he did quantum field theory in the curved space-time in the vicinity of a black hole. But it makes sense. Why does it make sense? Recall black body radiation. Black body radiation is radiation emitted by a body where matter is in thermodynamic equilibrium with radiation. And the radiation which has come into thermodynamic equilibrium with matter loses all its memory. It loses memory of how it was produced. What was the frequency when it was produced? What was its polarization? What was the direction in which it was propagating? There is absorption, and re-emission till it emanates from the surface of the body. And when it does come out of the surface of the opaque body, it remembers only the temperature of the matter with which it interacted. That is why Kirchhoff said in 1859 that the spectrum of a black body is a universal function characterized only by the temperature and no other property of the body. Similarly, Hawking radiation makes sense because the radiation is a thermal spectrum. Why does it make sense? All kinds of things went into the black hole. But the memory of what into the black hole is completely lost. All the quantum numbers and all the processes have been lost because the black hole is uniquely characterized by mass, charge, and angular momentum and nothing else. Therefore, the radiation remembers only the mass of the black hole. So it made eminent sense to Hawking that the radiation that can come out of a black hole or radiated by a black hole has a spectrum of thermal radiation, because that is the only thing that is consistent with the No Hair Theorems, that black holes are uniquely characterized only by their mass and angular momentum. Recall that when matter falls into the black hole, there is a tremendous loss of information. Black holes are uniquely characterized by their mass, charge, and angular momentum. The nature of the radiation emitted by black hole reflects this loss of information, just as the spectrum of black body reflects the loss of information. The spectrum of the black body at a temperature T will be the same whether it is from gold or silver or copper or sodium. All the other properties are irrelevant. In a similar manner, the radiation emitted by a black hole reflects the loss of information of what went into the black hole. The Hawking radiation makes sense because the radiation has a thermal spectrum and remembers only the mass of the black hole. Many people then tried to repeat Hawking's calculation, and they all confirmed it. No one was able to disprove it. So a very great discovery was made. And here is the temperature of the black hole as calculated by Stephen Hawking. The temperature of the black hole is inversely proportional to the mass. The temperature of the black hole is inversely proportional to the mass. Now let us put some mass into it and ask what should be the temperature in Kelvin units. So if the black hole has a mass of 1 solar mass, then its temperature will be 10 to the power minus 6 Kelvin. So colder than any temperature in the universe. So it will only absorb and it's not going to radiate. So the formula is the temperature of the black hole is 10 to the power minus 6 m sun divided by the mass of the black hole in Kelvin. Now suppose the mass of the black hole is not a solar mass, but million times smaller. Then the temperature will be 1 degree Kelvin. Suppose the mass of the black hole was only the mass of the proton. Then the temperature of the black hole will be billions of degrees. So the temperature of the black hole is inversely proportional to the mass of the black hole. Eventually, the black hole will evaporate away. The black hole will spontaneously emit and its rest mass energy will decrease. As its rest mass energy decreases, it will become hotter, it will radiate even more, its mass will decrease even more, the temperature will increase even more, there is a positive feedback, it will radiate faster and faster and faster until finally, poof, it will explode. And when it does, it has created a terrible problem for us, because what will remain is a naked singularity, which had till then been hidden, as Roger Penrose had conjectured. The singularity had been clothed by the event horizon. Now the black hole has disappeared. The event horizon has disappeared. And you're left now staring at you, the naked singularity. You have no idea what went into it. And that is serious trouble. Now you have to ask, has quantum mechanics transcended the cosmic censorship principle? In other words, it has not violated the cosmic censorship principle, it has transcended it. It simply says that I can remove the event horizon by quantum mechanical processes and show you where the singularity is. Now the question is, will an evaporating black hole leave behind a naked singularity? Well, the answer is not absolutely clear yet. But if it did leave a naked singularity, it will introduce an additional element of uncertainty in physics over and above Heisenberg's uncertainty principle. Remember, in Heisenberg's uncertainty principle, we are willing to accept that you cannot measure both the position and momentum of the particle simultaneously to arbitrary accuracy. So there will be an error in the measurement of both, and delta x, delta p must be greater than h bar by 2. So we are willing to accept that, at least everywhere, most people, Einstein never accepted it, but we are willing to accept the principle and start using quantum mechanics. But here matters are much worse, because the particles emitted by a black hole comes from a certain region. You don't know exactly where it is coming from. It comes from a region where the observer has a limited knowledge. He cannot definitely predict the position or the velocity of the particle or any combination of the two, which Heisenberg allowed. All he can predict is the probability that a certain particle will be emitted. So remember, all you can say of thermal radiation, the probability of emission of the frequency nu and nu plus delta nu is this. The probability of absorption is this. It's not a statement made with certainty. In Heisenberg principle, uncertainty principle, you can say a certain combination of position and velocity, I can make a statement that it is coming at least from that region with that velocity range. You are not allowed to make even that statement. You can only make a probabilistic statement. So there is a new element of uncertainty in physics over and above Heisenberg's uncertainty principle. In an article that Stephen Hawking wrote soon after his great discovery in Scientific American, he said this in conclusion. He reminded us of Albert Einstein's famous sentence, God does not play dice, God does not gamble. This was his observation expressing his displeasure with Heisenberg's uncertainty principle and indeterminism of the new quantum mechanics. Now, God not only plays dice, but he throws them in places where you cannot see the dice. This is what Stephen Hawking has said. God does play dice, but he throws them inside the event horizon so that you can't see the dice. So that is the second element of uncertainty. If no hair theorems are correct, in particular, if black holes are uniquely characterized by their mass, charge, and angular momentum, then black hole physics appears to be in serious conflict with quantum mechanics. This is known as the information paradox. I do not understand this very much, nor am I equipped to understand papers that are published on this subject. To the extent I've been able to understand, this is what the information paradox is. Imagine that the initial matter that formed the black hole, matter of the star which formed the black hole, was constructed from a pure quantum state which are describable by specific quantum numbers. That is a state with what is called as vanishing von Neumann entropy. Don't worry about what this von Neumann entropy. Please remember only this statement in blue. I construct a black hole with matter in pure quantum state. All right? The thermal radiation produced the black hole has a huge amount of entropy. And it's independent of how the black hole is formed. It only knows the mass of the black hole, nothing else. Therefore, black body radiation has enormous amount of entropy. So you started with a pure quantum state with zero entropy. a definite quantum state, and what you're getting out is thermal radiation with enormous entropy. Quantum mechanics requires that the evolution of the system is what is known as unitary, or the quantum entropy must be constant with time. So since something went into the black hole with a very definite quantum, in a very definite quantum state, any information that you get out of the black hole must also correspond to a unitary evolution, or the entropy must remain constant. And since initially the entropy was 0, there cannot be any entropy now. This is the information paradox. People are still arguing about it. Every now and then people claim that they have solved it. Stephen Hawking himself claimed that he had solved this problem. He said that there is information that you can get out of the black hole, but other people are not convinced. As far as I'm concerned, all I can tell you is the jury is still out. But just to give you some idea what is the direction along which people are thinking about, may I say this? The thinking is the information about the collapse is somehow encoded in the Hawking radiation. We are normally used to saying in black body radiation, there is no information. All the information is gone. Only the temperature is there. But suppose the Hawking radiation is different from thermal radiation, and there is information encoded which you could decode, then you're okay. Now this requires a revision of the No Hair Theorem. No Hair Theorem says black holes are uniquely characterized by their mass, charge, and angular momentum. But if there is information coded in that tells you what went into the black hole, then there are hairs. So you cannot say black holes have no hairs. They have quantum hairs, whatever that may mean. To put differently, the black hole horizon has some sort of gravitational memory. People still cannot quantify it. What is this memory and how is this memory stored? Soft hairs or quantum hairs on the horizon represent quantum microstates in this line of thinking. These microstates define the quantum state of the black hole. So the moment you can define the quantum state of a black hole, then you can argue, is it a unitary evolution or not? It is therefore conceivable that the quantum state of the black hole is determined by how the black hole was formed. That way, the quantum state has a memory of everything that went in. And therefore, the radiation by quantum processes will have encoded into it this information which you can then decode. So let me repeat this by saying that I'm not going to blame you if you didn't understand what I said just now, because I myself don't have a very clear picture of this. But don't worry, the last word has not been said about this information paradox, which does represent a serious conflict between quantum mechanics, as we now know it, and gravitational collapse. Who knows, when a proper quantum theory of gravity is discovered, this paradox will go away. The great Ludwig Boltzmann, one of the greatest physicists of the 19th century, committed suicide and died. Among his many great contributions to physics was the notion of entropy. Entropy as being the number of microscopic states corresponding to a macroscopic state. So if I have n boxes and I give you m billiard balls and I ask you to distribute these m balls into n boxes, there are a number of ways you can do that, and the logarithm of that number of ways is what he called as the entropy. The formula he wrote was S is equal to k log W. And that is written on his gravestone. So this is a photograph of Ludwig Boltzmann's grave. This is Westminster Abbey in London, very close to the Houses of Parliament. This is where, for centuries and centuries and centuries, all the kings and queens of England were coronated, where all the kings and queens of England were buried. This is where Isaac Newton is buried. This is where Paul Dirac is buried. Great poets, great playwrights. There's a statue of Shakespeare here and so on. There, Stephen Hawking, when he died a couple of years ago, was cremated in Cambridge. But the urn containing his ashes were interred in Westminster Abbey, where Newton and Dirac are buried. And on his gravestone, on the floor of Westminster Abbey, this is what is engraved. T is equal to h bar c cubed divided by 8 pi g kb times m. So this is Stephen Hawking's final statement. Well, the remarkable story of stars and singularities is by no means closed yet. It began with Ralph Fowler in Cambridge, then Chandrasekhar in Madras in 1928, Barder and Zwicky in 1934, Lev Landau in 1938, Oppenheimer in 1938-39, Roger Penrose 1964, Zeldovich 1972, Stephen Hawking 1974, and the story goes on. In the next lecture, we shall switch gears. We shall discuss the formation of neutron star binaries, two neutron stars going around a common center of mass. It turns out that astronomers have discovered such systems, and they have been used as laboratories to test the predictions of the general theory of relativity. So the next lecture, I shall discuss the formation of neutron stars in binary systems and also tell you about the various tests of general relativity that have been performed using this binary neutron star system. Thank you very much.